See here. So what are GANs, guys? Generative adversarial networks. Okay, so which are also type of neural networks for generating synthetic data. So what is synthetic data? We have already discussed about synthetic data, which is fake data that we are going to generate or create. Okay, so this generative adversarial networks will be containing two components, and first one is generator and another is discriminator. Okay, so as this is a neural network, we have to use TensorFlow or PyTorch. Okay, as it is having high level, high computational operations, we are going to use TensorFlow or PyTorch. Okay, so see here, what is generator here? So the generator will generate the fake data. Okay, resembling the real data. That means which looks like original data, but it is not original one. It is a fake data. Okay, and discriminator. So what is discriminator here? Discriminator will divides or discriminates whether the data is fake or real. Okay, so generator will generate the synthetic data and discriminator will discriminate whether it is original or fake. Okay, this is how these GANs work, generative adversarial network. So see, the training process will be involving two steps. One is first we need to train the discriminator and then we need to train the generator. So this is the structure of GANs. You can see here how we are going to. Okay, so in neural networks will be having forward and backward propagations, right? So we are initiating forward, backward, and we'll initialize neural networks, then loss function, then using generator we are going to generate real data. Next, we are going to generate fake data. Next, after getting results, we are going to discriminate input and again create fake data, and we are going to plot real and fake data. So this is the architecture that we have for GANs, structure of GANs. Okay, this is structure of GANs. Next, how we are going to implement this generative adversarial networks. So I think you got to understand about GANs. So let me show you architecture also. GANs architecture. See here they have compared this using the classic analogy. They have compared this generator as counterfeiter. Okay, and discriminator as FBI agent. So where counterfeiter is constantly looking for new ways to produce fake documents, okay, that can pass the FBI agent's test. So this is how same generator and discriminator. So what is the generator goal here? It will maximize the likelihood that the discriminator misclassifies its output as real. So it is based on probability. And now here discriminator goal is optimized toward a zero point 0.5. So the min max problem comes here. So this is the architecture you can see. Latent space, generator, generator image, data set, and real image. We are going to give real image and it is going to generate some image, and discriminator will decide whether it is real data or fake generated data. So this is generator architecture, and this is discriminator. Latent place, generator, and generator generate image. These three includes generator, and after generating images, this real image, generated image, and discriminator, again the result real or fake. So this comes under discriminator architecture. So the architecture is divided into two components. One is generator and one is discriminator. Okay. So the generator looks like this. You can just create a class generator and you can develop the generator. But for discriminator, it is a neural network. Okay. So it is a simple CNN. So it is a simple convolutional network. Okay. So please observe the architecture here. Sure, ma, I'll show you the generator architecture. This is discriminator, right? So this is generator architecture. Okay, ma'am. So have you gone through? So you should understand this. This GANs, generative adversarial networks, is one of the generative model. So we use this GANs for generating synthetic data. So why we are, yes, it detects real or fake. So why we are using these GANs to generate synthetic data, and why we are generating this synthetic data is, so sometimes collection of data is it is time consuming and cost consuming. Okay, so whenever we want to collect more data to train the model, so manually collecting is difficult. So in that case, that is what I'm saying, synthetic data means fake data, which looks like real data. Okay, for example, if we want to train a model on brain tumor. Okay, so brain tumor, so it is difficult to collect the real brain tumor images of so many people, right? So if we want to train a model, we need to have a so much image data, that may be lakhs of images, MRI scans, all those things. Okay, so whenever we want to train those models, like generative AI models with huge data set, then we are going to create or generate this synthetic data, and then we'll train the model on the synthetic data. Okay, so that is why we use these GANs, and it will be having two components. One is generator and one is discriminator. Generator will generate the fake data, and discriminator will distinguish between real data and fake data. Okay, clear? What is the purpose of GANs? So once again, please go through the architecture. Okay, so now let's see how to implement this GANs. Okay, for image generations, we use these things, GANs. So guys, let's discuss about types of GANs. So we have types of GANs for image generation. So let me show you. So this is GANs architecture. So there are so many types of GANs that we have. So here you can uh, see here in the jigs for jigs, it is very clear that how it works. Generative adversarial networks. So we are going to give real images and then random input we are giving. So randomly the generator will generate fake images, and now discriminator will get updated and it will give you the results like this, real or fake. Okay, so let's see here, and we know how this generator and discriminator works in Max. Next, types of GANs. See here we have types of GANs. So one is vanilla GAN. So vanilla GAN is a simplest type of GAN. So which can both are built using multi-layer perceptron. So it is you must be knowing multi-layer perceptron in neural networks, MLP, and we have this optimized algorithm called optimization algorithm called stochastic gradient descent. So you can just know what are the types. You can just again dig deeper into the types of GANs and what are the types that how we can use these things. And again is C GANs, which is conditional GANs, which will just add additional conditional parameter to guide the generation process. And next, deep convolution GANs, DC GAN. Okay. So for image generation, we are going to use this DC GANs, deep convolutional neural networks, adversarial networks. And next we have Laplacian pyramid GAN. So this is to generate ultra quality images. Okay. So ultra quality images. Next SR GAN, super resolution GAN. So low quality, which will increase the resolution of low quality images. So this is how. So these are the types of GANs that we are going to use according to our problem statement. Okay. So according to our problem statement, we are going to use this, and let's see how to build this GANs arc. Okay. So go to Google Colab. Okay, take a new notebook. New collab notebook. Okay. So today's topic is GANs, right? GANs. So we have so many other GANs, guys. Text to image generations, text generations, data augmentation, and video frame generation, face generations, deep fake GANs. So there are so many types of GANs. Cycle GAN. Okay. So that means you can convert one type of image to another, and you can convert sketched images to realistic images. Okay, that way there are so many types of GANs are there, and these can be used in many scientific and industrial applications like drug discovery, which can generate new molecular structures for drug development, and 3D object generations. Nowadays we are dealing with 3D models for gamings. Okay, 3D GAN which will generate 3D images, and medical image synthesis. As we discussed, we can generate MRI scans, synthetic MRI scans, MRI or CT scans. Okay, so next, what are the challenges in using these GANs? So challenges. Okay, so first thing is generator. So there is a challenge called generator produces only limited diversity of outputs. Okay, produce limited diversity. That means maybe if it generates no all the faces can all the images can look similar. Okay, that means low diversity will be there. So that is one of the challenges. And next, so if you want training stability, GANs can be difficult to train since generator and discriminator, they are going to compete. Okay, so they are going to compete, so it is difficult, and evaluation is difficult because it is difficult to evaluate that. Evaluation is difficult because to measure how realistic the generated data is, how realistic the generated data is. Okay, so these are the two main challenges that we are going to deal with this GANs. So let's work on implementing these GANs. Okay, implementing simple GANs. Implementing simple GAN for image generation. Okay, So first what we need to do, we need to install Torch. Okay, so we are going to use Torch. Let me install Torch. Next, so let me install Torch. So we have installed Torch. Okay, next Torch Vision. Okay, next Torch Vision. So let me install it. Torch Vision. So Torch Vision is already there, and Matplotlib also will be there. Okay, so now import. So now import all these things. Import Torch. Okay, next import. See here. So the code is generated. Import torch.nn as nn and torch vision dot datasets data loader transforms. So all these things we don't need it. Let me take whatever is needed. Okay. So import torch dot optim as optim. Next import torch vision. Next this data loader is no need. So next transforms to transform the image, and this is no need. Next we need to import matplotlib. Okay, to plot it, to plot the images. Import matplotlib dot pyplot as plt. Okay. Now what we need to do is we have to set device and hyperparameters before running it. We have to set device and hyperparameters. So before that you need to select this GPU acceleration, guys, for to train the model. Okay, run type you should change to GPU. Save it. It is connected now. So let me give device. I'm going to set the device so that is configuration. Okay, device equal to torch dot device, and next we need to add hyperparameters. So to fine tune, we are going to use this hyperparameter. These are generally like 0.002, and batch size we need to mention to train a model. Batch size equal to, let's give 64, and epochs, let me give 10 epochs. First we'll give 5 epochs, then we'll see. Next, latent dimension 100. Okay, so now we set the device. Why torch is not defined? Okay, now it is done. Next, guys, now we are going to load one data set. Okay, so load uh, like fashion. Okay, so we are going to load this data set, fashion memorized data set. So yesterday we worked on VA is on handwritten digit data set, right? So now we are going to use this fashion data sets, and now I'm going to use transform to just transform the data set, and then we need to initiate data loader. Okay, now initiated data loader. Okay, data loader dot utils. So it is generating the date code, guys, you can see, and this is how we need to give the. Okay, now we are giving root as data, and it has to download in data the data set. So now we are going to download the data set is downloading. Okay, so extracted data now. Okay, now print data. So I think data, right? The directory is data only. Yes, name data is not defined. So here it is data. Here it is downloaded. Okay, in raw. Yeah, this data set is downloaded. So you can check here the data set. So it is in JSON files, bytes. So the images, labels. So we have collected the raw data set. Okay. So there is no need to print it. So this is our raw data. So we cannot give the print here. So anyway, we have downloaded the data set. So here is the data set. It's a raw data set. So now what we need to do now, we need to define generator. Okay, define generator. Define generator. Before generating, we can also print this. We can get some samples. Let me print some samples. So get some before initiating this. Just getting some samples from the data set. So plot. Let me give plot some samples. Okay. So now real batch, data loader, figure size given. Next, I am show schema. So what is the error we are getting? Invalid shape for image data. So the real batch size figure I have given. Figure, figure size. So let me give another code. Figure, comma, axis. Figure, comma, axis equal to lt dot subplots. Okay. So I'm giving 3 comma 3 and figure size I'm giving 8 comma 8. You can also give 6 comma 6 like that. Okay. So your choice the figure size, and now for I, let's enumerate. So this enumerate function will just add, what it will do, it will just add index to the array. Okay. It's just dot flatten. Okay. So now ix dot data loader accesses of extract image and display. Commute cmap. So see here the fashion dataset containing these sample data set that this is. Okay, so these images we are containing in our data set. Okay, so we are displaying it. So now we have extracted the images, and these are the sample images that we are. So as this is a fashion data set, now we have apparels, and the apparels looks like this. So with this we need to train the generator, and the generator will generate fake images like this apparels. So basically the clarity and the pixels would be low. Okay, so now our data set is containing like this. Next, let us. So see here our data set contains clothing like shoes, shirts, bags like this. Okay, so now let me define the generator now. So this is the data set that we have taken, and they are all in grayscale only. Okay, to get the more information. And now define the generator. Define the generator. So how we are going to define our generator? Give class generator, and I am initiating within it self. Next, self dot model. So what is the model we are using here? Torch, and then sequential and linear, rectified linear unit. Yesterday I told you why we use this rectified linear unit to keep it in a scale. And linear, you can give dimensions. And then dot relu, and next 784. So I can give here 256 comma 28 pixels. Okay, 28 pixels, and I'm giving tan h here, and we are using forward propagation. Next, return self dot model x dot, let's give me view of. So this is how we define the generator. So we got some invalid syntax. 128, and then dot linear. Yeah, I think linear it is. L is capital, comma. Where did I forgot comma? So now we have defined the generator. Now what we need to do? Again, we need to define discriminator. Okay, define discriminator. So now we are going to use this discriminator as, so for better extraction we are going to use CNN, guys. Okay. Let us ask Gemini so that it is, we are initiating discriminator. Next, let's take again the dimensions. Leaky relu 0 comma 2, and again linear n dot linear 1 comma, again sigmoid, next. So this is a simple discriminator. Next, same, we need to give def self dot model image. So here I'm going to give image. I can not implementing, it's just image. And now I need to give view image dot view dot image dot size of 0. Okay, 0 comma -1. So now let's run this discriminator also. So next, what we need to do, we need to initialize models, losses, loss functions, and optimizers. Okay, models, loss functions, and optimizers to keep it in a scale. So now generator equal to, you have to call the generator dot to device. Again, we need to call discriminator. So this to the discriminator. Again, device. Next, we need to take criterion. So this is loss, guys. Okay, Adam optimizer and loss we have taken here. So now run it. Something is wrong. Generated init one missing positional argument. So there is some dimension. Okay, latent dimension we didn't give. Okay, next. So now we have initialized losses and all. Now we need to train the GAN now. Okay. So step by step, train the GAN. Okay. So for epoch in range of epochs, image size of 0, and now we are going to take train discriminator. Okay, now we are going to train discriminator. So batch size optimizer. Next to device fake labels. So now real loss. Okay, let's see real loss equal to, so this thing just real loss criterion. So next real loss criterion discriminator fake image is equal to generator real loss, and we missed some fake loss generator. So from here we have train the generator. Train generator. Z equal to dot. So real labels, fake labels, real loss, and also we need to give fake loss here. Okay, fake loss is given. Next, what we need to do? Total loss equal to real loss plus fake loss. Okay. Next, we need to initiate optimizer, and now we need to print it. Okay. Now, if it is print G loss, so we got an error. Module discrimination is required. The forward function not implemented. So did we miss any forward function here? So in the discriminator, what we did here in the discriminator, forward function. So now we have changed discriminator. Trying again, we are getting the same loss. Forward function. So okay, here it is suggesting some changes. Rename discriminator to disc. Let's see. So again, we are getting expected all tensors to be on the same device. CUDA on CPU. So let me check this. Now we got fake images. No shapes matching here. So mat 1 and mat 2 shapes cannot be multiplied. So we have to change the shapes pixels. So this is the generator. So we need to change 128 to 256. And generator. Now again we are going to run this. So how many epochs we have given? Only 5 epochs, right? So it is getting trained. It is giving discriminator loss and generator loss. So it is taking 100 as batch and increasing 100 for each batch. Okay, it is got trained on 5 epochs, guys. After training the generator and discriminator, we have trained the generator and discriminator on 5 epochs. That means 5 iterations with 100 batches. So now we have to generate and display images. Okay, generate and display images out of it. Let's see how our image will just with the torch, fake images, figure size, again CMAP, mute, access off, and plt.show. So plotting subplots. So here we got generator images like this. So as it is very low epochs, only 5 epochs. So the training is like this. It has given blurry images. Okay. So instead of permute, I'm going to use generated fake images of I dot squeeze. Time x dot I am show fake images of I dot squeeze CMAP equal to gray. Okay, now let me keep it in commenting. So can't convert CUDA device to MTAG sentence. So okay, so it is not working. So now it is working. So these are the fake images. So our generator, how it is working now, it is generating the similar images but with very less pixels. Okay, that means we need to train the model more and with more and more epochs. So that means our GANs have insufficient training has done. Okay. So now let me improvise it by using any for 10 epochs. Okay. Guys, can you try it with more epochs? So the data set itself is not clear, so it is having very low pixels. That is why we got this generator. It is trying to generate similar images, but the training is not sufficient. You have to give more, like 10, 20, 30 epochs like that. So 30 epochs like that. Now let's change it to at least 20 epochs. Let's see how it works. So where is the epochs that we have given? So here, let me give 20 epochs. So we have changed to 20 epochs. So let us try on 20 iterations, guys. Now, generator, discriminator, initialize the models, loss functions. So let us wait for 20 epochs. So meanwhile, it is training on 20 epochs. So let me explain you how the code works, guys. So this gener how do until here you're clear, right? So we have imported all the libraries which are needed, required, and we have set the device to CUDA, like that we need to use the CPU or GPU. And next we loaded this fashion IST dataset, okay, from transforms.compose, and I'll also try to explain this, the code, okay. So let me explain each block. So guys, it is explaining each and every code. So what we did, so we have imported torch, right? So this line imports PyTorch library. As we have discussed, we are doing this using PyTorch or TensorFlow. Now we are using PyTorch library. Okay. So what is this PyTorch? PyTorch is a deep learning framework that provides tools for building and training neural networks. Okay. So it handles things like tensor operations, automatic differentiation, and GPU acceleration. Okay. This torch will take all the functionalities of the PyTorch. So that is what here about PyTorch. Next, so this import NNN module from PyTorch. So what is this NNN module? Neural networks. Okay, NNN means nothing but neural network. See here, this module provides building blocks for creating neural networks, and it contains classes for defining various layers. We'll be knowing fully connected layers, convolutional layers, and activation functions in our neural networks. If you go through, so that is what here NNN dot linear, it is selecting the linear fully connected layers, okay, to create layers. Next, so why this line optim module from pytorch. So why we have used this optim? So which contains optimization algorithms. We know about optimizing algorithms, right? So gradient boost, stochastic gradient descent, adam booster, all these things are grade which are optimizers. Okay, so these optimization algorithm we have imported from torch optim. Okay, next to torch vision. So you can see here what is this torch vision library. So which is an extension of pytorch that is specifically focused on computer vision tasks. Okay, what is computer vision task? Which deals with images and videos, right? Detections. Okay, training with images, loading images, image transformations, all these things comes under computer vision. So this is an torch vision is a library which is an extension of pytorch that specifically focused on computer vision tasks. Okay, so what this torch vision contains, this package contains data sets. See here, it provides data sets, pre-trained models, and image transformations. Okay, so like this, and again from torch vision only we are extracting our data set called, so torch vision dot data sets, and from the data sets, see here, so this data sets module provides easy access to standard computer vision data sets. What are the standard computer vision data sets it is having? This mnist, cipher 10. So these are the names of data sets. ImageNet, so already standard data sets it is having. So from that we are downloading this fashion mnist. Okay, so that is the data set name. And next, transforms. Why we are using this transforms? Okay, so this transforms model produces tools for what? Pre-processing images. Pre-processing means what? So whenever we just initiate a project, if we collect the images, and then next step is image pre-processing. That means we need to clean the images. Okay, how we are going to clean the images? Such as resizing, cropping, normalization, and data augmentation. Okay, what is data augmentation? Is nothing but increasing the data with the trying with other angles. Okay, like rotating, you can rotate in four directions so that your data set will get improved and the model will get trained more accurately. Okay, so this is what happening here with this torch vision dot transforms module is providing you all the pre-processing techniques for pre-processing images such as resizing, cropping, normalization, and augmentation. Okay, and as usual we know matplotlib. Okay, matplotlib is for what? To just create visualizations such as graphs, charts, and images. So to display that image we are using these plots, so that is why we have imported this matplotlib. Okay, clear? So this is the purpose of all these libraries, why we are importing here. Next, so next also let me explain this simple code also. So what it is doing here, it is setting up the device. So setting the device, see here, the code is responsible for setting the device that is used for training neural network. So see here, torch.device is a function which creates a device object. Okay, so which specifies the computations will be performed on a GPU or CPU. Okay, so whenever we give this CUDA, no, it will enable GPU is available. Okay, checks if the GPU is available, it is going to use GPU. If it is not available, else it will just work on CPU only. Default, by default, it work on CPU, but it will check if GPU is available, then it will run on a uh, GPU accelerated runtime. Okay, runtime. So that is why we select runtime type also. Next, defining hyperparameters. Why do we define these hyperparameters? See here. So these are the basic things for a deep learning to train images. So these are the basic terminologies we must know. LR means learning rate. Okay, which means it controls the step size during the optimization process. Step size means what? Weights, nothing but modals weights. For during each training iteration it will just controls the learning rate. That means it should not take more or more images or more batches at a time. It will be giving stable training, see, but might take longer to converge. So based on the search results, the learning rate has a large impact on the stability and performance of the GAN. It controls the step size, okay, like how many steps or how many batches it has to take and train it. Next, batch size. You know about batch size? So batch size is nothing but a batches, a group like a group of 64 images, like, so 64 images is one batch, okay, like that we have to create or we have to divide our data into batches. Now epochs. So epochs is what? It refers to number of times the entire training data set will be passed through the model. So entire data set, for example, if you are having 1000 images, then each batch is 64. That means how many batches it will get? So those many batches has to get trained 20 times. That means 20 iterations. Okay. So epoch is nothing but a multiple training iterations. That means 20 times we need to train each batch so that the model will learn. Okay, next, latent dimension. So this latent dimension we have discussed yesterday about the latent space. Okay, so whatever the decoded output will be in the latent space, so that we can get more realistic image from this latent space. Okay, so this generator uses this latent space to create the fake data. Okay, so this fake data, see here, it is compressed representation. We have given 100, so that is a compressed representation of the input data. Generator can manipulate to generate new outputs. Okay, so by referring this latent dimensions, the generator will create new outputs. Okay, see here, these hyperparameters are crucial for training your GAN model. So not only GAN model, any deep learning model, these hyperparameters are crucial, guys. So whenever you are dealing with images and training images, these hyperparameters you have to set up so that it will be stable training will be done. Okay, see here. So the dimension of the random noise used to generate the data affects how well a GAN learns to generate realistic data. So, okay, so how GAN learns to generate realistic data is depending on your hyperparameter tuning. That means you have to give good hyperparameters. So this is what about setting up the device and giving defining hyperparameters. Okay. Next, so another block of code what we have written here. So next we have loaded the data set. How we have loaded the data set and what are these dimensions? How did we normalize and how we converted into tensors? All these things let me explain you. Okay. So here it is. Now we define how to transform the data. So we have used these transforms. Why we have used these transforms? For transformation of image. Okay, in the data set, multiple transformations together, and two tensor transforms dot two tensor converts images, okay, into a image format. This pillow library we know, right? For image manipulations we use this pillow. Initially pill image format, okay, initially our data set is in images, then it will just convert it into tensors. That means numpy arrays or PyTorch center tensors. Okay, so that means our images are converted into arrays. That means numerical representations, so that model can understand. Okay, it also scales the pixel values to the range of 0 comma 1. That means normalization will be done here. It will scale pixels into range of 0 comma 1, all the images should be on same pixels. Okay, next normalize. So this normalize 0.5 0.5, what it is, it will just normalize the pixel values of the images. It subtracts 0 0.5 from each pixel value and divides by 0 0.5. Why? Because for effective scaling. Okay, so that everything will comes under a range of -1 comma 1. So that is how the normalization will take place. So this normalization helps see improve model training by making the data have zero mean and standard deviation of 1. Okay, so then the scaling will be done and it will comes into standard dimensions. Okay, so because of the image, because the images are grayscale, no, so why we convert these color images into grayscale? To get more information or to get more features from the images, we just convert color images into grayscale. Okay, this is one of the image processing techniques while pre-processing the images. Okay, so that is what we have normalized the images and converted into grayscales. So now see here how we are loading our data set. So we are initiated the data loader from torch.utils. So what it is, it creates an iterator that provides data in batches. So now we have to, so it handles shuffling and batching the data. So we have given 64 batch size, right? So in that case, it will just, it divides the batch sizes. Okay, based on the batches. And here we are loading, okay, from torch only we are loading this data set, and we have downloaded this data set and kept it in a root equal to data, and here the data directory has created, and in that we have this raw images. Okay, next train equal to true means what? Indicates that we are loading the training data set. That means with the data set we need to train the model. Now download equal to true. If the dataset is not found in the specified root directory, it will automatically download from the internet. Yes, we have downloaded it, and the folder has been created here. Next, transform equal to transform applies the transformations we defined earlier to the images. What is transform here? It will transform images into same pixels. Okay, so that is what happens. And batch size equal to batch size. What is the batch size that we have given in the hyperparameters? We have given it to 64. So that means each batch will contain 64 images. So now shuffle equal to true. Why we are giving this? That means images has to get shuffled. Okay, not only the same images, it has to get shuffled, and for each epoch, the images will be different. Okay, this will helps in improves the model's ability to generalize. Okay, so to be in a scale and to be in a standard way, so it is going to, it will improve the model's ability to generalize. See here, and this code, this whole code, what it is doing, it is just loading the data set from torch, and it is transforming and converting the images into tensors and arrays. So as the model cannot understand the images itself, it has to be converted into numerical representations like arrays and tensors. Okay, so this is how our this is how we have downloaded the data set. Next we'll see, and this, if you know that this is for plotting the images, and again we are extracting from the arrays, we are extracting the images. Okay, because our images have been converted into tensors and arrays, right? So again from tensors we are extracting the images like this. Commute, flatten means what? It will just uh, replicate. Okay, if it is in arrays, it will just convert it into images. If it is in images, it will just convert it into arrays. This flatten. Okay, flatten, what it will do? 1D to 2D, 2D to 1D, it will converts. So now we are extracted the images from the arrays. So like this, our sample images in a grayscale, it is looking like. Okay, the apparels we are having, t-shirts, shoes, okay, shirts, sandals and all. Okay, next, so how we define this generator. So let's see the simple generator, how we have defined it. So see here, so this you might be knowing, class is nothing but oops method. So first we have taken class generator. So that means we are creating a new generator object and we are defining it and with the self. Okay, which takes self. Self is nothing but instance of a class, and here latent dimension is the input. Okay, so now this line is calling initiation for neural network module, and nn dot sequential. That means in neural networks, it is that allows you to chain together different layers. That sequential is nothing but the sequence of layers, right? So it will chain together different layers. And here, so what are the dimensions that we have given? Those are vector sizes. Okay, vector of size 256. That means our images have been converted into linear vectors. Next, we have used this rectified linear unit activation function. Okay, it will introduces non-linearity to learn complex patterns for a neural network. Next, this is nn dot linear 256 is a dimensional vector to another 256 dimensional vector. That means it will transforms the 256, 256 to 256. Next, we have again initiated this rectified linear unit, and then here we have given, we are transforming 256 dimensional vector to vector size of 784. That means this is the pixels 28 by 28, which is the size of a flattened fashion image. Okay, flattened means what? Converting 1D to 2D or 2D to 1D, right? Next, here we are using tangent activation function hyperbolic, which outputs values between -1 and 1. That means normalizing the pixel values. By using this tan h, we are just normalizing the pixel values. Next, this forward method, why we are passing this forward method? You know about forward propagation in neural networks. The input passes through the generator networks. So in a forward way, it has to pass. The input has to pass in a forward layers, not from the backward. In a sequential model, we'll just pass our input in a sequential manner from forward. So not backward. So in forward propagation, we are giving our input. See here, it uses linear layers with the activation functions and final tan h activation. The output is reshaped to a 4D tensor. Okay, representing a batch of grayscale images. So now all these vectors has been converted to 4D, and now we are getting as images, grayscale images. So this is how our input will goes through. We can pass the input to generator. So this is the defining of generator. Simple code, simple sequential layers, neural networks. Okay. Next, I hope you are clear about generator. And next, discriminator. So same way, discriminator also we have defined with neural networks. So same way we have taken a class discriminator, same as generator, and we have initiated the self. And what is the input here? Init method, discriminator object, and same sequential layers we have initiated, and a fully connected layer with size 28 28, that may be 20 to 56. And then we have given activation function negative slope of 0.2, so that it will learn more complex patterns. Okay, so these are all the dimensional vectors. Here also dimensional vectors, and in the last we are applying sigmoid function. Okay, to just to just get probability 0 or 1. So the probability of input being a real image. So it will just give the probability of a real image. If it is 0, it might be slight real. Okay, like that. It will give 0 and 1. In between 0 and 1, it will just give us the probability of input, whether it is real image or not. So that is what the purpose of this sigmoid function here. And same way, input is passing in a forward way. See here, forward method defines how the input data is passed through the discriminator network. So the input is representing the batch of sizes. So and again, image is converting into flattened vectors here. Image size of 0 minus 1. It will just pass through the sequential layers, and the output is returned, which will be probability that the input image is real one or not. So it will give the probability of the real one. So that is what discriminator here it will works. And now, so okay, 20 epochs it is done. Okay, now let me explain you about loss functions, loss function and optimizers. Okay, let's see how this loss function and optimizers work. So first we are initializing the generator. So whatever we have written the functions to the generator or classes, we are just calling and initializing to device, and we are giving latent dimension as input. Okay, and we are moving the generator model to the specified device that we have given. If it is GPU available, it has to be run on GPU, otherwise it should run on CPU. Okay, same way for discriminator, and we are defining the loss function here. Okay, so this BCE loss is binary cross entropy loss. There is entropy called, which is noise. Okay, which is noise in the neural networks. So this is binary cross entropy loss. We are defining the loss. So common loss function it is for binary classification problems, which is suitable for GAN setup. Okay, that means, so why it is binary? It has to discriminate. Okay, whether real or fake, right? So binary discrimination. That's why we have used this binary cross entropy loss here. Next, optimizers. What are the optimizers we have used here? Adam. So Adam is the optimizer algorithm, optimized algorithm we use to update the model's weights during training. See, based on gradients of the loss function. To reduce the loss, we have used this optimizers. Setting the learning rate. So we have given learning rate as 0.002, so that it will just standardize, and weights are adjusted during the optimization. So based on learning rate, the weights are get adjusted during the optimization. So this is how we have defined model, losses and optimizers. Okay, to improve the training model we have optimized, and criterion we take it as a cross entropy loss to reduce the loss. It's a loss function. Okay, now again, so this is written two times. Okay, now again, so how did we train the GAN model? Okay, now we are set. We have defined generator and discriminator. Now we need to train the model. Okay, so how we are going to train it? In a loop. Okay, so epochs, what how many epochs we have given? We have given 20 epochs, and for each epoch it should take image, and it should see here the inner loop iterates through data loader, which provides batches of real images from the dataset. So whatever the dataset we have taken, it will take input as real images, and this function returns index for for a data for each iteration. Okay, it will add index, that's count, it will add count to the images, enumerate function. So next, what is happening here? Batch size is determined from the current batch of real images. And we have initiated optimizer because during the training, the optimization is a must for both the ground. It will just represent labels for real images and all the functions like loss function, entropy loss, everything we have given here. And now here, what we are doing here, noise vector is created, which will act as input to the generator. So this generator again take from the latent space. From the latent space, it will take the dimensions and it will generate the image from that fake image. So this is how we have given optimizer losses, and we are giving loss as a backward input as backward. So now the generator training goal is to generate images that are indistinguishable from real image. So to make the discriminator think fake images are real, that means it is assuming, it is making discriminator to assume that it is generating real images. So and next in this we have defined epochs and discriminator loss. So this code implements the GAN training process. See here, for every 100 steps, that means 100 batches, it outputs the current epoch. That means whatever the discriminator loss and generator loss, no, it will allows you to monitor the training progress. So it will printed in 4 decimal spaces after tensors of a Python number. Next, now this discriminator and generator networks are trained in alternating fashion. That means batches to distinguish between real and generated images, which can see this generator learns to create images that can fool the discriminator. Okay, to make discriminator think like it is generating real images. So that is what the training loop here, it is happening here, training loop. So done with 20 epochs. So now, so after 20 epochs, it is slight better than before, guys. So now we can at least we can just able to see that they are apparels. It is created same similar. It is generated similar images. Okay, so this is how it is generated. And the last code, like it is matplotlib codes. So we are just giving figure size and plotting. So now let's try to generate, try to plot the So last Gemini. So now I want to display fake and real pages. Labeling. Same code it is giving. So now what we need to, we have to label, like which is label them as real or fake. Right. So let me plot real images quickly. So here are the real images. Now let me print fake images. Plot fake images. Okay, now we are plotting fake images. So these are the fake images and these are the real images, guys. You can see the difference. There are slight difference between fake images and real images. So I can give title here, so that ELT dot title. These are real images. Real images from our data set. That whatever the data set we have given, no? So from this, so randomly, see here, shuffled images we are getting. Why this ELT didn't worked out? Okay, now set title as real images. So now it is displaying as real images. Okay, same thing here. Title fake images. So these are the fake images. So fake images generated like this. So if you want to know high accuracy, you can just run, or you can just train the model with more and more epochs, like 50 epochs. You can train on 50 epochs, and then you can get the difference, guys. So this is the slight difference we are getting for real images and fake images. So this is the purpose of GANs. So that the architecture is simple. So it is containing two components. One is generator and discriminator. First, you need to get all the required libraries here, and you need to import all these PyTorch and required libraries. Then you have to set the device. Next, you have to load the dataset from transforms from data loader, and then you have to extract your data images, and you have to display. Then next you need to define the generator by using simple neural networks, and same discriminator with linear neural networks. You can also, if you want to enhance this model, you can use CNN, guys. Convolution neural networks also you can use. Here we have used simple neural networks. Okay, and now the loss and optimizers to optimize the training, and then you can train the GAN by giving epochs and setting the parameters, real images, real loss, fake images, fake loss in a forward layers. So then you can just run, or you can just train the model in 20. So we have trained in 20 epochs, so we got slight difference. So that you can just train your model with more epochs, so that your accuracy will be high. Okay, the pixels would be more clear. Next, you can generate and display images like this, fake images. And if you want to discriminate, you can just give the simple coding with plotting, and you can just give title real images and fake images, so that you can observe the difference here. So also in the last, you can just add accuracy of the model also. Okay, accuracy of the model. You can also test the accuracy of the model. You can also plot accuracy of the model. So by just giving print. Okay, so like this, you can just give accuracy, and there is some. So you need to change its size, guys. You can just try it out. You can just try the accuracy of the model, how accurately it has generated, similar to the fake images, similar to original images. So I think you are clear about GANs.